If when is needed, I will do that. Right now, look at here. Okay.
Sir, I have a question.
Yeah. So can we discuss at the end? Or yeah,
Yes,
tell
yes,
me.
sure.
Yeah, if you are, I mean, quickly tell. Then subsequent
Yes.
question I will take at the end. Yeah, tell so.
So degeneracy would lead to like exchange energies. So why stopping degeneracy would be a good thing for a molecule? I don't understand.
No, I did not get your question. Why stopping means? I do not understand.
Like if the electrons are if the electrons are exchanged, like if there is degeneracy, so that will lead to exchange energies, right? So like
No, I'm not
uh
talking about the exchange energy at all. Why do you I mean, confuse exchange energy? There is no exchange energy here. I think you're confusing, right?
acha, okay.
Here you see that D9 system, there is no exchange energy at all involved here. This single electron,
Okay, yes, yes,
as
I
a
got you.
ninth electron, can occupy either of the orbital. Right? There is no exchange. I hope you got it.
Yes, yes, I got
Okay, now let's go. I mean, I will give some time for question at the end so that we'll be able to finish we have reduced the number of the topics, but I want to explain you properly. So at the end, I will give time. You note down your question, you can ask me. Right, now look at here, what I have shown here. There is in the middle, what I have shown, it's a OH. There is an octahedral geometry. On the other side, forget about the notation that I have given. Forget about it. It doesn't come there. This is comes in the group theory or what we say the point groups. Don't bother about that. Simply look at the octahedral geometry. In the octahedral geometry, there are two possible way of distortion. One is an elongation, that is here what I call. Another is a compression. Already I have shown you, right? Already I have explained you that what I mean the elongation and compression. Let me turn on my camera and I will show you the model. I hope you will be able to see. Now you can see that this is assumed that is a perfect octahedral. Perfect octahedral model. There is a delay is there. This is a perfect octahedral model. Okay. Now what we are going to do is that I'm going to show you what actually here I have shown and in the diagram elongation or my compression. Right. First, let us talk about the elongation. Now look at here. What I have here is now you can see that my axial bond is longer than the equatorial bond. Right. What I have done is that, say for example, to make you understand, I pulled the ligand. I've stretched out the ligand along the z-axis. But basically, we are not going to do that. Right? Don't mistake that. Why Sir is telling that we are stretching and pulling. This is to make you understand. Right? This is what we got z out. Right? Or stretching along the z direction. Now, on the other hand, there's another possibility that I have gone to the extreme left-hand side. That is what we call a compression. Right? Now, what will happen is here, if you carefully look at the model that I've shown, right, my axial bond is shorter with respect to my equatorial, right? Look at the same way I am showing here that the axial bond is lower. Is basically what you are doing is you are compressing. In the previous case, what you have done, you are zooming out, right? Stretching out. So there are two geometry comes into picture now. Two geometry comes into picture. That is number one is what we have is a compressed geometry, and another one is an elongated geometry. Both are basically a distorted octahedral, right? Nothing but of a distorted octahedral, right? Now this is what I have shown here, right? What I have explained in the diagram, you can look at here. Now the same thing I have again. I am showing here what I call the tetragonal distortion. Where I am talking about tetragonal distortion can be up to either it can be compressed or it can be elongated, stretched out. So what I have shown the compression, the 3D model that I have shown is a compressed one. Again, I'm not going to explain. The same thing can be done with the stretching out. Now let's look at here. Okay. Now what I have taken here is that you keep in mind, in your background, what you should remember that the Jahn-Teller theorem. That is basically the electronic degeneracy. That is the sole cause of this kind of a distortion. So that's what we are looking at the examples. Now look at here, copper 2 plus. That's what I have the D9 system. D9 system. I already explained you. There exists here electronic degeneracy in the EG orbital, right? This one electron can be either here or can be here. That's what we talk about the degeneracy. Now, what is happening? I mean, nobody dictates or nobody goes and tells that this bond, the axial bond, should stretch out. Because of the electronic degeneracy, what is happening here? Say, for example, you take a copper hexafluoride, hexafluorocopper, let's you take here. Now you have your axial bond length is 227 picometer. On the other hand, your equatorial one is basically your 193 picometer. Right? This is basically what I'm going to call JT distortion. JT distortion, or what you call the Jahn-Teller distortion. That is basically initially a regular octahedron turn out to be converted into a tetragonally distorted geometry. Right. Now what is happening? Right. Now what is happening? Now look at here. Now if it is a tetragonal distortion, I hope you understand here, right? I put it in a different way. Now you look at here the energy level, right? Yeah, the energy level. Look at this one. Yeah, there's a delay. Initially, what I have shown here is my left hand side. That is my dxy, yz, xz. That is basically a T2G orbitals. On the other hand, my x squared minus y squared and z squared is basically my EG orbital. That is a typically a regular octahedron. Now the distance between these two, what we call the del O. Okay. Now, because of this electronic degeneracy, what is actually happening? A further splitting of the d orbital, that is what I mean, the T2G and EG orbital further undergoes splitting, and you get, right, what we have, z squared and then x squared minus y squared. Right? This is in the case of your elongation. Right? In the previous class, I mean, before your midsem, I mentioned this briefly. I pull out, right? I mean, stretch out this ligand along the z direction. As a result, what I have is the interaction between, what do we say, electronic interaction between the incoming ligand and the d electron is less. As a result, what will happen? The orbitals which has z component undergo lower in energy. That's what is happening here. Right? I hope you're getting. Right? I repeat once again. What I do here, that physically to explain you, what I do, I stretch out the ligands along the z axis. Okay? Now, or in other words, the incoming ligand along the axial direction is at a far distance. So, the electronic interaction between your central metal d orbital and the incoming electron is less with respect to your axial ligands. As a result, what happened here is there is a splitting in the orbital, that is the T2G and EG orbital, wherever the Z component is there, that lowers in energy simply because the interaction between the ligands in the Z direction is less with respect to the others. As a result, what we have, your dz squared is lowest in energy and x squared minus is little higher. And the same is the case here. Now at the end, what we have, del O is far greater than del 1. Delta O is far greater than del 1, that is here in the EG orbital, and far greater than the del 2, that is here. I hope you are getting how the orbital undergoes splitting when you have an electronic degeneracy. As a result, what happened to the geometry? A tetragonal distortion. Now, I hope I got right. Now let's go to the other way around. Right now, I thought I will ask a question and then break that, but time is limited. So look at here. So what happened? If you understood in the previous case, you will be able to easily understand this line. Here, what we do is that there is a compression along the Z direction, right? As a result, what happened? The ligand, incoming ligand, has a greater interaction. As a result, the Z component goes upward. all the orbital which has a Z component goes upward. The others, the orbital that doesn't have the Z, that's low in energy, right? So just opposite of the previous one, elongation versus compression. Now here itself, let me explain. Right? I hope you got it. What I mean by elongation and compression. Both are tetragonal distortion. Both are tetragonally distorted. Either you the elongation or your compression. Let me go here. Right? Now what I have here is that let me take the model. Let me take the model and then I will show you. Just hold on a minute. Right. Let me show here. No, just a minute. Okay, right. You can see the model that what I have shown the elongation. No, just a minute. It's a compression. I will take out put the elongation. Then I will be able to explain you what I mean. What I mean that other geometry that I take it. Okay. Now look at here. This is elongated geometry. Tetragonal distortion, along this axis, elongation takes place. Now, what I do is that there is no ligand along the axial position. Now, what I got, can anyone unmute your microphone and tell me what I got? This is a square planar geometry. A square planar geometry, you got it. Right? That's what we have. That's what we. If I don't have any ligands here, there is no incoming axial ligand, or other words, I have removed the ligand in the axial position in the Z direction. What I get is basically a square square planar complex. A square planar complex. Okay, this is how we get the. Or in one way we can say that extremely distorted. Square planar is basically a extremely distorted. Right. Now we come here. I have put together D1 versus D9. Right. I hope you could see that D1 versus D9. What is happening? In the case of your D1, what is happening? In the case of D9, what is happening? Right. In the case of D9, that's what we have taken your copper 2+. Say, for example, what I have already explained, right? Basically, what happens? Elongation. There's again a tetragonal distortion. On the other hand, if you have a D1 system, there what is experimentally observed is that compression, right? Is that compression? So in both the cases, what is happening is that distortion is taking place. One thing you need to remember that Jahn-Teller distortion will never say you about the nature of distortion. It tells about whether the particular system will undergo distortion or not. Whether it undergo a elongation or it undergo compression, this is not the job of the Jahn-Teller distortion. So if we want to understand who decides this compression and the elongation, that is an advanced topic, right? In the Jahn-Teller distortion, what it says? It says that the system which has an electronic degeneracy will undergo distortion. That's all. After that, the Jahn-Teller distortion is at your level, it's a silent. So if you want to further study that, we will go to the advanced. Right? But I hope you understand how the D1 versus D9 system, there are the distortion taking place, either the elongation or compression. Now you will have a question, sir, how do I know this? So what are the systems that will undergo distortion? Let's talk generally about the distortion. We are not going to talk about the elongation or about the compression. That is beyond your syllabus. Now, what I have shown here is, right. Now, you can see here, you can look at here. So wherever the red color is shown, red color orbitals, say for example, the red color D3 and a D5 and a D8 and in the D6 at the low spin complex. Okay. And then, of course, obviously D10. Okay. your D5, D3 and D8. So these will not undergo any Jahn-Teller distortion simply because there is no electronic degeneracy. How do I say? Go back, recall what I taught, right? D3, only one option. D5, yeah, only one option. For what one option talking about? The filling of the electron, alignment of the electron, right? That is, so there is no electronic degeneracy. In the case of D8, we'll talk only about the EG orbital, And obviously, in the case of your D6, we'll talk about the T2G orbital because there is no further electron. D10 are completely occupied. So you can easily find it out that which are the system, I mean D system, will undergo distortion or not. I mean whether it will undergo distortion or not. Looking at the electronic configuration, we'll be able to explain. The reason behind is electronic degeneracy that you need to remember, right? In the case of the blue color, look at the blue color, the D4, right? I hope you can. The D7 in the low spin complex, D7 low spin complex, and then a D9. Obviously, we have seen the D9 system, copper 2+ system. There you will be able to see a significant distortion in the geometry. On the other hand, the normal distortion, right? There is a normal distortion in the sense not of a significant distortion, but still it is distorted. But compared with your D9 system, say for example, the distortion in the black one, right? Whatever the black that I have shown here, say for example, a D1, a D2, a D4 in the high, low spin, and a D5 in the low spin, and D6 in the high spin, and D9 in the high spin. Sorry, D7 in the high spin. So these will undergo distortion, but the distortion is very limited, right? The normal distortion with respect to or less distorted with respect to your other system, which I have shown here as a significant distortion. I hope you got it, right? Now look at here again at the same thing. Whatever I have explained you, I have extended. Yes.
So, can I ask so?
Yeah, can we discuss at the end?
So actually in D2 why there is
no, can we discuss at the end?
Quick questions, sir.
Pardon? Okay, right. I will take the question at the end. I will give 5 minutes at the end. Right. Now look at here what we have. Now, here I have shown everything together. That is your octahedral, your tetragonal distorted geometry. There is a, let's say, distorted geometry. And then what we have is the square planar geometry. So how do you get it here? Now look at here. Initially in the T2G and EG. And then when you come to a tetragonal distortion, the each orbitals, the EG and the T2G are further split, but the energy gap is limited. And then when we talk about here in the square planar, as I have shown earlier, there is no incoming ligand along the Z axis. As a result, what happened? Your Z component, if you carefully look at here, your Z component is, I mean, very low energy. Because there is no incoming electron in the Z direction. As a result, these are rest of them, right, proportionally increases, right? So now you will be able to see that the del O, what is happening in the octahedral, and then what is happening in the tetragonal distorted system, and then in the square planar, right, what is happening, right? I have given the values, how much is the energy gap between the dxy and z squared, that is 0.656 delta O, and between z squared and x z and y z, it is basically 0.086 delta O, right? Yeah, right. Now I give you an example. Usually I used to ask the student to solve this, right? I mean, because we don't have a time at the end, or after I finish, I will give enough examples. I think the previous class I have given a couple of examples. Here what I have shown, is that the question is, what is the crystal field stabilization energy? The CFSE of FECN6 3 minus, right? The last class we calculated. I hope you can recollect, right? There are the two possibility. There is whether we can have it a high spin or low spin, because this CN minus is a strong field ligand. As a result, what will happen? There will be a, can anybody, if there is a strong field ligand, then there must be a
Low spin complex.
low spin complex. The pairing takes place. Yeah, low spin. There's a pairing takes place. Your crystal field stabilization, yeah, CFSE is as shown here, right? Yeah, it is here, right? Crystal field stabilization. Now, the second example what I have given here is that what I have given here is that, yeah, hexacobalt, and what is a spin state? This you know that this your water H2O is a weak field ligand. As a result, you need to consider how the splitting will take place, how the electron will fill up, and then you can calculate your CFSE value accordingly. One thing you need to remember, as I mentioned in the previous class, you should remember the pairing energy. Pairing energy should be taken into account. Once you know that number of the electron and you know the nature of the ligand, and then you fill up the electron and then calculate the value. Okay, right. I'm not going to spend much time there. I will ask my tutorial teachers. You have your tutorial on Wednesday. I will ask them to give you enough example to work out on the class in this week, right? Because we have only two weeks, this week and next week. I will ask them to give you enough examples. So please attend your tutorial class. Now we'll come to that. What are the applications of the crystal field theory? Right. There are four things that I have enlisted here. That is, number one is the lattice energy. Number two is the ionic radii, and then enthalpy of hydration, and then fourth one is site preference of spinels and inverse spinel. This is basically we'll teach with material chemistry, preferably, most probably. We may not be able to address this, but I will briefly mention this to you, though we will not study the material chemistry. Okay, so now what I'm going to explain you is the lattice energy. Lattice energy of first row, or say for example, I have given you sodium chloride. Look at the table, and then magnesium fluoride, manganese fluoride, iron fluoride, copper fluoride, and nickel fluoride. Now look at here. Look at this. The measured value that is experimentally observed. That's what here. And then calculated value. The lattice energy can be calculated using the Bond-Landis equation. I hope you might have come across in the JEE syllabus, not in a class 2. If not, I mean, the lattice energy can be calculated with the help of a Bond-Landis equation. So we are not going to calculate this. We are going to see here what are the application of crystal field theory. Number one is the lattice energy. Right? You can look at here. The sodium chloride, the calculated value and the experimental value is almost same. Not almost, it's exactly same. Magnesium fluoride almost same. Manganese fluoride also close to each other. There is a difference, plus 0.7, plus 7 and plus 24. When we come to the iron, copper and nickel, a huge variation, right? If one would theoretically expect that, what should expect that what should be the calculated value and the measured value, experimentally observed value should be same. But in the case of, it is not the case, a significant deviation in the lattice energy for the first row transition metals. That's what I'm going to highlight here. That's your iron, your copper and your nickel. That's a significant difference. Let me put in this way, right? I hope you can see the diagram now. It will be more easy for you to understand. Look at here. What I have plotted is the increasing atomic number. My right hand side diagram. Increasing atomic number for the first row trans metal complexes. That is a chloride, right? Here, what I have plotted is a lattice energy kilojoule per mole. This is, I think you should have come across in your JEE syllabus. I remember that when I said, I mean, one involved in the JEE, this was a typical question several years back. Now it may be very common thing. There is the double hump shape is coming there. If you look at the calcium, manganese, and then zinc, right? The calcium, manganese, and zinc, right? There's a delay. The three things that have encircled, almost in the perfect line, linearly increases. The lattice energy linearly increases as you move from the low atomic number to the high atomic number. But in between that, there is a large deviation. A large deviation is there. So who is causing this deviation from the theoretically expected value? Now, there is only one way. If you can read that, right? If you consider the CFSE value for either calcium 2 plus, that is D0, that's manganese 2 plus, that is D5, zinc 2 plus, that is D10. What is the CFSE value for all these this system? The calcium, manganese, and zinc. Can anyone unmute and tell me?
0.
0, right? So whenever there is no contribution in the CFSE, it almost falls perfectly in a line. It's a linear variation. On the other hand, whenever there is the CFSE is there, then there is a large deviation, right? As anticipated, a smooth curve is not seen. Instead, your double hump curve is obtained. Now, if you calculate your lattice energy by considering the CFSE, it is well matches with your experimentally observed value. So you can explain the deviation from the regular trend of the lattice energy only by considering the CFSE, which basically comes from the crystal field theory. Okay. Second one, what I have is that the ionic radii. What we have, right? The same way we look at this. Look at the diagram that I have shown on my left hand side. The increasing atomic number, again the same trend, right? I mean the same thing I am using. There I use the lattice energy. Here what I use is the ionic radii, right? What you will expect is that as the atomic number increases, what should happen? There must be a regular decrease in the ionic radii, because basically charge increases, atomic number increases, effective nuclear charge increases. One should expect a regular trend, but this is not happening, right? Calcium, Ca2 plus, Mn2 plus, and zinc 2 plus falls almost linear, right? But there is a deviation. There's a significant deviation. When you look at this, not only for +2 oxidation state, it happens with a +3 oxidation state also, right? So this system that I have shown is a halide complexes that we are talking about. Now in the case of your +3, I'm bringing something more, right? The low spin and high spin complexes. You can read from there. For a strong field ligands like Cn-, a different trend in the variation is observed. That is D6 here. That is what I have shown here. This is basically a strong field that I have written here. On the other hand, this trend is for your weak field. Right? How do we explain here why this is happening? Right? Why this change in the trend? Not only in the case of your double hump, when you talk about here in the +3 oxidation state, it's a completely different behavior. The strong field and weak field giving a two different trend. The ionic radii trend is two different way it goes there, right? Now you can see, you can read this one. Why does the ionic radii decreases and then increases? What I am talking about, a decrease and then increase. Look at here, a decrease and then an increase, and then again a decrease and then a increase. This can be explained, there's a delay is there. This can be explained only by the crystal field theory, where filling up the electrons, right? Go back to your d orbital splitting. the T2G and EG orbital, you can read it there, right? Whatever I have written here. So the T2G and EG orbital, and then how the number of electrons fills as we move from your D0 to D5 and then D5 to D10. That is basically what I D0 to your D5 and then your D10. Okay, so how these electrons are filled, you need to consider the strength of the ligand, whether it's a weak field or a strong field ligand. Then you will be able to explain the observed trend, right? Let me read it for you, right? As the EG orbitals point directly towards the ligand, the repulsion between the metal electrons and the ligand electron will be higher than the normal, leading to a eventual increase in the ionic radii. That's what happening in the V2. Okay. Now, in the case of a strong field ligand, such a cyanide, there will be a steady decrease till T2G is completely filled. That's what I have shown here, right? In the here, the cobalt 3 plus, this your T2G 6, right? A steady decrease till all the electrons are filling the T2G orbital, and then again it goes on increase. I hope you understand how the incoming electron, how it fills the orbital, that how it contributes to the ionic radii. It's not a magic, it's not a hypothesis, it's a experimentally observed, right? The incoming electron, depending on the nature of, depending on its nature, whether it's a strong field or weak field, then it's become high spin or low spin. Accordingly, what happened? Your ionic radii changes. This can be explained only with the help of crystal field theory, right? Okay, I hope you got it. If there is any question, I will give a 5 minutes time at the end. You can ask me. The similar to the lattice energy, there is another one. What we have is the enthalpy of hydration, right? I'm not going to explain much of here. Very similar to your lattice energy calculation. Enthalpy of hydrogen also can be calculated. Here also there are deviations. This deviation can be accounted only by considering your CFSE. That is basically comes from your CFT. So the CFT, crystal field theory, the application, of course, there are several magnetic property, color of the complex is there. Apart from that, what I have explained, number one is the lattice energy, the double hump behavior, as also in the enthalpy of hydrogen, and then ionic radii. These are two very important things that cannot be explained with the help of any other theories. Right? Only when you bring the crystal field theory, or in other words, the CFSE value, you will be able to account for your the deviation or the observed the properties, right? I thought I will finish my magnetic property, right? I'm not able to do that. I will briefly tell you, and then I will give a 5 minutes time, right? Now, what we're going to talk about, very important one is that the magnetic property of a transition metal complex. A brief explanation is given here. That is a diamagnetic or paramagnetic. Schematically, I have shown here, right? The diagram A is a magnetism of, basically what you do is that what we call this a Gauss magnetic balance. There's a balance called Gauss, G-A-U, right? Y. Gauss magnetic balance. In the balance, what it is a old method, right? Now you have your advanced instruments to measure the magnetic property. Now, this was the earlier day. It was what happened is that there are two magnets. In between that, what you have to hang your samples in a wire. Now, which is connected as it is shown here in the diagram, the A to B to C, right? Now, when you switch on the magnet, this complexes or the substance or the sample that you have in your vial is paramagnetic or diamagnetic. What will happen? The diagram it shows here. So the B basically what happened? It pulls in, right? As a result, there be a deflection in the meter, the magnetometer, that will show a deflection. So you will be able to find out this is paramagnetic. On the other hand, diamagnetic, it repels. As a result, there will be a change in the magnetometer, and then you can find out from that is a diamagnetic. This is very qualitative. Now you can quantitatively find out magnetic susceptibility, or what we call the magnetic moment in terms of Bohr magneton. Right, in the coming slides, it is there. Right, Bohr magneton. Okay, right. I will finish with this one. There are two components in the case of how the magnetism comes into picture for a metal complex. With that, I will finish, and then I will give a time for you to ask question. Number one is that fundamentally we learned that electrons spin its own axis, as well as it spins around the nucleus. There are two components for the magnetic moments. One is the spin only magnetic moment, and number two is the angular magnetic moment, angular component. That is, the angular momentum component comes because it's not only spin its own axis, but also spin around the nucleus. So there are two components that comes into picture whenever we talk about the magnetic property of transition metal complex. So here in your topic, what we'll talk about is only the spin only magnetic moment that you should have studied in your JE syllabus. So that I will continue quickly. That's very simple calculation. Then I will finish the magnetic, and then we'll go to the next topic. Now, if you have any doubt, unmute your microphone one by one, and I will explain. Go ahead.
Excuse me, sir.
Yes, Bajaj.
So can you show the slide number 50?
Slide number
50.
50. It's quite noisy. I'm not able to hear. Which one?
50.
50. 50.
So
This one. This one.
yes, yes.
Right. Yeah.
So, yes. So I did not.
No, I did not get your question. Bajaj, can you tell me what is your question? Can you hear me? I'm not able to hear. Can you hear me?
Yes, sir, you are audible.
Yeah, I mean, he asked some question. Yeah, others can ask question. Maybe if others have a question, please ask. I will answer. Anybody? No question?